Welcome back. In this video we're going to continue our discussion on permutations, and we're going to talk about even and odd permutations. Now this video kind of encapsulates the important idea that every permutation can in fact be written as a product of a number of two cycles. Obviously they're not going to be disjoint anymore, but the number of two cycles is going to be either even or odd, and it turns out this determines whether the permutation itself is even or odd. That means no matter how you break it up into two cycles, you'll always get an even number if it's an even permutation and an odd number if it's an odd permutation. Okay, so let's dive straight in and look at our first theorem. So our first theorem says that every permutation can be written as a product of two cycles. So what we're going to do is to prove this, we're just going to do a little construction and we'll work on one disjoint cycle, because if we can turn one disjoint cycle into two cycles, we can turn any of them into two cycles, and then the product of the whole lot collectively will still be a product of two cycles. So we just need to consider one disjoint cycle. Okay, so let's just write it down as kind of general as we can be. It's going to be A1, A2, up to AN. Okay, now the proof is really easy here because I'm just going to give you a construction and we'll see really quickly that it actually works. So here's how it goes. Essentially you start from one end and we write them down as two cycles starting with A1 and then AN, A1 then AN minus 1, all the way down to A1 and then A2. Okay, so let's see how this works. In fact, let's write down an extra one here. Dot 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 A1, A3, then A1. Might as well put my bar. A1, A2. Okay, so if I just multiply this thing out, you can see that this is going to work. So I'll get A1 first. Now I'm going to track A1 through the system. So A1 goes to A2 here. And then A2 does not actually appear in any subsequent permutation. Right? A2 does not appear in any of these at all. So A1 just goes to A2. Now we'll track A2. A2 in the first one gets mapped to A1. A1 then goes to A3. And then A3 does not appear again. So it becomes A3 here. Similarly, now I'll track A3. Doesn't do anything in the first one. A3 gets shifted to A1 here. Then it'll get shifted to A4 and the next one along that you can't see. And so that will become A4. And the whole thing just sort of works out nicely and we get back to our cycle very quickly. Okay, so you can always write down a cycle of any length as a product of two cycles in this way. Just write down the first element in each one, and then write down the remaining elements in reverse order in each pair, and the whole thing just works out. Okay, so let's do it for 1, 2, 3, 4, 5, shall we? E.g., 1, 2, 3, 4, 5 by this method gives us 1, 5, 1, 4, 1, 3, 1, 2. Notice a cycle of length 5 turns into 4 two cycles, and that's always going to be the way. A cycle of length n becomes n minus 1 two cycles. Cool. Great, so that's cool. So we've established that every permutation can be written as a product of two cycles. We're going to build up to a pretty big theorem that says that the way you break it up is going to always be even or always be odd, depending on whether you've got what's called an even or an odd permutation. So I'm going to state this little lemma first, which actually is going to bear the brunt of the work for this theorem. And it says that if epsilon is equal to a product of two cycles, so beta 1, beta 2, up to beta r, where the betas are two cycles, then r is even. Okay, so the lemma says that if I can write the identity as a product of two cycles of R, two cycles, then it must be true that R is even. Okay, so we need to prove this. Okay, we're going to actually attack this one by induction. So first off, R is not equal to 1, as a two cycle is not that entity. Okay, a single two cycle can never be equal to that entity, so we can guarantee that R is not equal to 1. If R equals 2, we are done. Okay, so we're going to set up an induction hypothesis here, and then we'll start working on our proof. So hypothesis is for all 1 between n and r, epsilon equals beta 1 through to beta n implies that n is even. So we're going to assume it's true for everything less than our current r. Right, so let's see how this works. So we've got a little bit of an idea here, and again, it's hard to sort of motivate this without just doing it. So what we're going to do is we'll show that essentially we'll have this situation here. No matter what, it's going to look like this. And let A, B be the last two cycle in our product. And we're going to show that it can be written as, we're going to define some little tricks of manipulation that essentially turn this into A something, 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 etc., etc., where the only A present is in the last one, is in the first one, sorry. Okay, so this here is the only A. Now that's not possible, right? There's no way this can be the identity, because this product on the left here transports A to something, whatever else is in its pair with it. Okay, because there's no other A, that can't be cancelled out, so there's no way this can be the identity. So if we can come up with our transformation that will push it across there, this is a contradiction. Unless somehow we reduce to the identity along the way. Okay, so how's that going to work? So what we're going to do is we're going to focus our attention on the last two here. And we're going to look at all the possible configurations we can have, and we can see if we can redesign them so that, or re-express these, so that in each case I have this thing where the only A is on the left. The idea there is well then to sort of propagate that construction along to the left, and what we get will happen as part of that. So let's look at the possible forms that the last two cycles could take. Okay, given that AB is the last one, we're looking at the possible things that the one before it could be. Well, and one possibility is that it's equal to that entity. Another possibility is that it has A in it. Remember, AC and CA are the same thing, so we don't need to consider them separately. And this one here, if we expand that out, well, A goes to B, B goes to A, which goes to C, that equals ABC. Which in turn, if I just rearrange this slightly, is BCA, which equals, now I'm going to undo my expansion here, equals BA times BC, using my breaking up into two cycles idea, and now I'll write the first one as AB. Okay, you can see what I've done here is I've taken my product, And I've just manipulated it so that I have just a single A on the very leftmost position. Okay, what's the next possibility? Next possibility is that we have B in one of them. Okay, and then we can manipulate that again. That, if we multiply out, gives us ACB, which I'll write that as CBA. Just shuffling it around, it's the same thing. And that in turn is equal to AC BC. Same idea, it's 2 cycles, but now the only A is just in the very first spot there. And the other case that we could have is that we could have 2 things that are different altogether from A and B. And that, because disjoint cycles commute, can just be written directly as A, B, C, D. Okay, so here's the point. The point is, no matter which of these 4 forms I have here, well, the 3, not including the identity one. No matter which one of these 3 forms I have, it's equivalent to a product of 2 cycles with only a single A in it. So, how does that work then? So if I now go back to my larger construction, so we'll let the last, try that again, we'll let the last 2 cycle beta R be equal to AB. Then either one of 2 things. So our first case is that those last 2 are the same thing and it's the identity. So either beta R minus 1 times beta R is the identity, in which case I'm starting from my statement here. If that's the case, then beta 1, beta 2 up to beta R minus 2 equals that identity, which by my induction hypothesis implies which in turn implies that beta R minus 2 is even, and hence R is even. Okay, so just quickly recap that argument. So we're making this assumption here that epsilon equals beta 1, beta 2 up to beta R. So that's just focus your attention here for a second. That's sort of what we're assuming to be true here. And now, our induction hypothesis is that for anything less than R, we know this is true. Okay, so that's our assumption here. We've assumed we've proved it for all values up to there, but not including. So now we're saying, all right, let the last 2 of these cycles be something something AB. Then, if the first case applies here, the one I put the green asterisk on, then those 2 will become the identity, and so our product of R 2 cycles has now become a product of R minus 2 cycles. And by our induction hypothesis, we have a product of 2 cycles equaling the identity where the number of them is smaller than R, and so that number must be even, which gives us R being even. So that is our first case where the 2 things collapse down into that entity. Otherwise, so now I'm just going to scroll up a little bit. Beta R minus 1 beta R can be written beta R minus 1 beta R equals A something something something, where X are not A. So now we repeat with beta R minus 2, beta R minus 1. Again, either that pair, this is after we've done the rewrite, either beta R minus 2, beta R minus 1 equals the identity, which implies R minus 2 is even. So let's do the intervening step, which means that beta 1 dot 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 beta r minus 3, beta r is the identity, which implies r is even, same logic as before, or we now have beta 1, beta 2, a x, 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 x equals the epsilon. So you can see what happens here, and I'm probably not going to continue it on because it's just going to get a bit tedious. But basically, every step, the A gets shifted further across. So it started being a member of the rightmost 2 cycle, and then we used our construction to move it across into the position 1 further across here. Okay, and then we repeated. So then either the 2 collapsed down, in which case we could use our induction hypothesis to infer that r was even, or we shift the A 1 step further across. And in its wake, on the right hand side, all these little x's, they're not a's. So if we continue like this, eventually the A is going to hit the very left hand end. And if it does, we don't have the identity, because if we did, there had to be another A somewhere else to make sure that A didn't get shifted by the transformation as a whole. Because if A was on the far left, and you imagine what the permutation as a whole does to A, no other 2 cycle will touch it, except for that very leftmost one, and that will shift A off A, and so you can't have the identity. So let's write a quick note as to what happens here. If this continues, as far as beta 1, beta 2, we have a product of 2 cycles with A only occurring in the first one. But this does not fix A, and we must therefore have had a product of 2 of these, 2 cycles, being the identity at some point during the process. Okay, because as soon as we get 2 of them actually multiplying to give the identity, that gets us out of this construction, because suddenly our product of 2 cycles has become 2 less. So now there are r minus 2 of them instead of r of them, and our induction hypothesis has assumed that for anything less than r, if you have a product equaling the identity, then there must be an even number there, and so we can be finished. So finally, we'll just note that our induction hypothesis is true for n equals 2, and therefore by induction it follows that it's true for all r. Is true for r equals 2, and therefore true for all r by induction. Okay, so hopefully that made sense. It's a bit of a hard thing to write down quickly on a video, but what it said is that now we've shown by induction that if we have a product of 2 cycles equaling that entity, then necessarily that number of 2 cycles must be even. And that brings us to the main theorem, which says that if alpha can be expressed, I'll just read the ones not in brackets, if alpha can be expressed as a product of an even number of 2 cycles, then every decomposition of alpha also has an even number of 2 cycles. So if one way of expressing it as a number of 2 cycles is even, then no matter what other way you come up with of writing it down as a product of two cycles, it will always be even. Okay, so that means if we were to write that out in longer form, that if we had alpha equals beta 1, beta 2 through to beta r, and gamma, or sorry, alpha again, equal to gamma 1, gamma 2 through to gamma s, then the theorem says that r and s are both even or both odd. Okay, so let's just prove this, and this one's really easy because all the hard work was done by our previous lemma. So we'll just start with making the left-hand side equal the right because they're both equal to alpha. I'm just going to put everything on one side because I know that something equals the identity is something that's useful to me. So using my socks and shoes, I'll get beta r inverse, which is just beta r itself, beta r minus 1, beta 2, beta 1, gamma 2, up to gamma s is the identity. Just remember when you invert a two cycle, its inverse is itself. That's why I haven't written any inverse signs in there, but I did reverse the order according to the socks and shoes property as I should. Therefore, by our lemma, r plus s is even, which is another way of saying, i.e. r and s are both even or both odd. Alright, so let's just have a quick definition to make sense of that. So we can now define what it means for a permutation to be even, and pretty simply, a permutation is simply regarded as even if you can write it down using an even number of two cycles, and similarly for odd. If you can write it down as an odd number, a product of an odd number of two cycles, then it's an odd permutation. Now it turns out that the even permutations form a group. Now I'm not going to prove this because we can kind of just do it very quickly out loud. How do we know? Well, if you multiply together two even permutations, then the product of those is going to be a permutation which also has an even number of two cycles to express it. Likewise, the inverse of a permutation of an even permutation is going to be that same product of two cycles written in reverse order. So the inverse is also going to be even, and therefore the even permutations form a group. The odd ones, however, do not, because if you compose together two odd permutations, then you get an even permutation, and so you've left your set, you don't have closure. So the even permutation is called a group, and it's called the alternating group of degree n. And we simply write it capital A subscript n. Okay, so one last little theorem to finish off, and it's to do with how big the alternating group is. And the theorem simply says that the order of an is equal to n factorial over 2. This is for n greater than 1. Okay, so the alternating group, basically the size of this, the number of even permutations that there are, is half of the number of permutations that there are total. Why is that? Well, if we take an odd alpha, then 1, 2 times alpha is going to be even. Okay, and so let's just take two odd ones to take alpha and beta to be odd. Then 1, 2 alpha is not equal to 1, 2 beta. So what this says is that if I take all of my odd permutations, they're never going to be equal to each other if I multiply them by 1, 2. So there are at least as many even permutations as odd. Because these two are both even, right? I've taken an odd permutation, I've multiplied it by a single two cycle, so the result will be even. Hence, there are at least as many even permutations as odd. Same logic works the other way, and at least as many odds as evens. If you start with 2 even ones, then you'll get the same result coming out. If we multiply both of those by 1, 2, you'll get 2 odd ones, and therefore there are at least as many odd permutations as even. Finally, that basically is telling us now that the number of odd and even permutations is equal. Given that the size or the order of Sn is n factorial, it follows that the order of the alternating group of degree n is n factorial over 2. Okay, so that's about all I want to say about permutations. Key information is that you need to know how to, let's just write this down. You need to be able to express a permutation in disjoint cycle form. You need to be able to express a permutation as a product of 2 cycles, and thereby classifying it as even or odd, and you need to be able to convert between notations and compose things naturally. Convert between matrix or cycle notation. Okay, so these are sort of just basic skills for working with permutations that you need to be pretty comfortable with. It's pretty often the case that you'll start by turning a permutation into disjoint cycle form. Once it's in disjoint cycle form, you can then calculate order, etc. Okay, so you can't calculate the order of a permutation until you put it in disjoint cycle form. Once you have, you can calculate its order. When you calculate a product of 2 cycles, you can classify as odd or even, etc, etc, etc. Okay, so that's enough for now. We will pick this back up next video, in which case when we'll be moving on to our next topic. So I'll see you later.